Hello everyone. I'm Masataro Asai, and today I present my SRIPS framework called CAP. I have two messages to share with the audience, which is first one is that decomposition is useful, maybe trivial to some of these ones. The ground macros are useful. This is a second message. So let's go to the decomposable problems. Assume we have this kind of assembly type problem in which the task is to assemble two drawers, B and D. This has two sub-goals, and this problem has two plans. Which the first one is that assemble the B first, and another one assembles D first. These kind of problems are known to be much easier compared to the non-decomposable problems because the planner do not have to resolve the conflict between the sub-goals. And such decomposable problems in which the products can be assembled independently can be divided into sub-problems, each with sub-initial state and sub-goals. These are easy, but we focus on this type of problem because although they are easy, the large instances which are 10 times larger than the standard IPC instances, for example, they are still unchallenging for the modern planner like FD. And in this standpoint, we developed a CAP planning framework which works on all IPC level instances and solves those large instances, and which uses decomposition and ground narrow macros. Oh, I'm shorter. And these ground narrow macros are different from the traditional lifted macros. And this framework is implemented as a wrapper for the standard planners, for FF, FD, anything like that. So we describe the overview of our system. It basically has two steps that uses this kind of underlying planners. And we tested 4 planners, FF, Llama 11, Probe, and FD with context-enhanced additive heuristics. And in these underlying planners, we can use different planners for each phases. However, for example, FF and FD Llama, but in this presentation and in this publication, we always use the same planners for simplicity. For example, we can always assume that these planners are FD Llama 11. A little bit quite old, but it's okay. And next, we further describe the details of this system. And the first step, decompose the problem into explicit PDDL definition of the sub-problems. And these are solved independently by the underlying planner, and then return to the CAP. The CAP converts these sub-plans into the ground macros, which have no parameters, which are narrowly and grounded. This is a distinguishing feature compared to the previous macro-based systems. And these macros are added to the domain definition, and the original domain is solved by the underlying planner in step 4. And in the final step, the macros are decoded to obtain a final plan. This overall system is a satisfying planner, which follows a simple divide and conquer approach. So this is quite similar to the HD, may not be, but and the factoring planning. And next, I will describe each step in detail. The first step, the problem decomposition, is something like this. Assume we have a too large assembly problem that cannot be solved at once. We try to decompose it as if, without knowing, it is decomposable. So it may not be decomposable. We don't care. Then we get these kind of sub-problems, each of which are smaller and easier. Each sub-problem has sub-initial state and sub-goals. The decomposition method is not that important. We can switch the decomposer, For example, we can use a trivial method like this. For each type in problem PDDL definition, pick the objects of that type, in this case, body of the droid, and then collect the other all objects which are not body, and then each subproblem has only one such product. It worked in this is an unpublished experiment, so it's not in our paper, but in our actual publication, we used the component abstraction method in Botea MS04. This finds a class-like structure in the problem definition. In the class-like, I mean those in the object-oriented languages like C++ or Java. And this is not my contribution. This is by Botea et al. And these are originally used for macro filtering, which is a completely different purpose compared to our decomposition purpose. And this is okay, we can use other decomposition methods. Then we get these kind of subproblems and solve each of them independently using the underlying planner. So quite simple. We get several subplans, and next we want to assemble all products in the problem, because the final plan assembles every product. And the intuition is to connect the subplans if possible. To do that, the natural conclusion is to create macro actions for each of these subplans. However, although it is intuitive, it doesn't work at all. So why it doesn't work at all? I'll describe it in detail in next section. So let's review the macro actions. These are the subsequence of actions composed into one action. For example, we have move AB and move BC. And this can be combined into one macro action, move ABC. These macros are created by merging the elements of the base level actions. For example, the parameters are approximately the union of the parameters of the base actions. This is technically not. And the preconditions and effects are constructed so that it cancels the intermediate effects. To use these macros, we modify the domain definition by adding the macro actions. And we call this a new domain as enhanced domain. And the same problem definition can be solved using this domain with standard planners. There are long history of macro-based planners back in the 70s, and there are also several recent planners such as MacroFF or MUM. And they mostly share the learning scenario, not all. This learning scenario is there are training instances which are easy and hand-picked and small, and the training instances which are difficult and large. These are the different instances. To find macros, the learner solves these training instances and induces macros from it. And then the learner uses these macros in order to solve the testing instances. The advantage of adding macros is a speed up. This figure shows the search space of simple Bloxworth type domain. Thanks to the dotted lines are the macro actions. And thanks to the added macros, the goal state can be reached in 2 steps compared to the 3 steps in the original domain definition. The bad point of this is the increase of the branching factor. Notice that the initial state has outgoing edges 4 compared to the 3 in the original domain. And another disadvantage is the increase of the number of actions. This is related to the common behavior of the standard planners such as FF or FD. Usually the lifted action schema is instantiated into ground actions with objects in the problem definition. This substitution increases the number of actions exponentially to the number of parameters. Like this example contains 9 ground actions. This is not. This is okay with the smaller number of parameters, but longer macros tend to have more parameters, and this sometimes make a trouble. For example, this move from mid to this macro has 27 ground actions. And in such cases, the FD made and the translation phase or the preprocessing phase may not finish, or the FF should be recompiled with larger max operators. And based on these backgrounds, the traditional approaches have filtered the macros based on their length. So these are typically up to 10 length 10. On the previous, And why does it happen? This is basically because lifting and learning. Lifting, which is generalization, is necessary in a learning-based scenario. This is because the macros learned in the training instances cannot be directly applicable in the testing instances, because the objects, in this case the color of the flags, are completely different. So the lifting is inevitable. However, we want to avoid it because lifting makes a problem. To overcome this issue, we all completely ignore the training instances, or do not use the training instances, and instead use the training instances, testing instances itself to find macros. We use them directly and avoid lifting, because the problems are the same. These action sequences are converted into narrow ground macros. The narrow ground macros are something like macros that has no parameters, and all preconditions and effects are grounded using the PDD constant section, and the names are arbitrarily chosen, and it has several desirable effects. The most important one is that one macro only results in exactly one ground action. And another one is that it has only smaller flexibility, and thus smaller chance of application and a smaller increase of branching factor. The summary is that traditional macros achieve speed up, but the number of actions increase and the lengths are limited because of the learning and lifting scenario. Our decomposition-based non-learning system do not require lifting, and instead use ground narrow macros. A long story short, these lifted macros do not work at all, and instead we use ground narrow macros. The fourth step is the domain enhancement, which adds these ground macros. And remember that the input can be non-decomposable, and in that case, the macros may not be used at all by the underlying planner. We don't care. And finally, we have this kind of meta-level plan which contains macro actions. We decode the macro actions into the base level actions. Simple. Now evaluation. We compared the standard planners against those planners wrapped by CAP. We have three sets of instances: IPC11 SecSat, and the IPC11 large, and the IPC11 learning testing instances. The large instances are created with the same generators, but with a larger parameters. Notice that the woodworking in the large instances have up to 81 parts compared to up to 13 parts in the IPC11 satisficing track. This is same for the IPC learning testing instances. This may be arrogant, but the IPC11 smaller instances, in this setting, the results are comparable because or maybe worse, because this was because there were several 20 versus 20 tie in particular in Burma and elevators and woodworking. However, in larger instances, we all outperform the base level planners. Note that the learning instances are solved with SecSat sensing with 30 minutes and 2 GB setting. And this is again unpublished results, but we tested the CAP with lifted macros, and the results were completely bad. So the lifted macros do not work. And also we compared the MUM and wizard and macroFF, but the results are clearly omitted due to the time constraint. And the conclusion is that ICAPS solves large problems without knowing whether they are decomposable or not. And decomposition is useful and ground macros are useful. Thank you very much.